All right, so we have this idea for a matrix inverse, but we don't know how to calculate it yet. So let's suppose that we have a square matrix A, so it has to be square to have some hope of having a matrix. And let's think about how we could calculate A inverse, assuming it exists. So if it exists, if A does have an inverse, then A times A inverse has to be an identity matrix of some appropriate size. Okay. Now I'm going to write it as if it's 4 by 4, but keep in mind that it could be any size depending on what size A is. Well, the matrix A inverse, it's some matrix. That means it since A has to be square, it's n by n. A inverse also has to be n by n, and this identity is going to be n by n. So A inverse is going to have n columns. So we could name those columns A inverse 1, and then A inverse 2, all the way up to A inverse column n. Okay, so each one of these things is a column for a column of A inverse. Now, if we use this to write down this equation again, we get A times all of these columns, like this, equals this identity matrix. All right, now in this matrix product, where does this first column come from? Right, so this is n rows and first column. Well, the first column comes from the first column of the matrix on the right and all of the different rows in the matrix on the left. So to work out this first column of the identity matrix, really what we need is our matrix A times A inverse first column equals this first column of the identity matrix. Right? So if we can solve this equation, then what our solution will be the first column of the inverse matrix. But we know how to solve this sort of equation, right? This is a vector with n entries. So we can solve this system just by forming an augmented matrix like this, and then row reducing. Okay, now we know that if there is an inverse, for A, it will be unique. And that means that this row reduction, there has to be a solution, and in fact there can be only one solution because inverses are unique, and so there's only one possibility for what this column can be. But if there's only one possibility, then that means that after you do this row reduction, so something shows up here, in fact it's going to be the column we're looking for, but what shows up on the left? Well, to have a unique solution, what shows up here when you do row reduction has to be all ones down the diagonal. In other words, when we finish this row reduction, assuming that the inverse exists, there will be the n by n identity matrix right here. Okay, so that's how we can find the first column. We can just solve this linear equation. All right, well now let's look at the second column. So that would be with a 1 in the second position, and that would come from using the second column for the matrix product. So that would give us A times A inverse second column equals 0, 1, 0, and then all zeros after that. The augmented matrix for that would be A augmented with 0, 1, 0, and then all zeros after that. And then we do row reduction again. And again, assuming that the inverse exists, we have to get the identity matrix on the left, and then the vector here that is our solution will be the second column of our inverse matrix. Well, we can do this for every row, and the last row is going to look like, every column. The last column here, that will come from the last column, the column of the inverse matrix that we use to get this, the last column in the product, is the last column of the inverse matrix. So our last one here is A times the nth column of the inverse matrix equals, and then the last column of the identity matrix, which is all zeros except a 1 at the end. So then the augmented matrix is going to be A augmented with zeros and then a 1. And then we do row reduction. And we, again, because assuming that the inverse exists, it's unique. And to get a unique solution, we have to end up with the identity matrix to the left here. And then to the right is the column of the nth column of the inverse matrix. Okay. Well, it's kind of annoying to have to do this n times, right? There are n different row reductions here. But if you think about it, I mean, what is different from row to row here? In the augmented matrix, the only thing that differs from row to row is what this vector, what the augmenting column is. And then so that's different. Of course, the results that you get are different. But what about the row reduction? Is that different? Well, the operations that we're doing for this row reduction are the operations to turn A into the identity matrix. But for each one of these row reductions, we're always reducing A to the identity matrix. So these row operations will actually be the same. And that gives us a really nice trick to do all of these row operations at once. So instead of augmenting our matrix A with each column of the identity matrix individually, let's do it all at once. Let's augment A with the entire identity matrix like this, right? Because this is 1 and then all zeros, and then 0, 1 and then all zeros, and so on over to 0, 0, all zeros, and then a 1. Right? That's what we're augmenting with. So really, each column of this augmented thing on the right are the individual columns for our previous row reductions. Okay, so now if we do a row reduction that turns this A on the left into the identity matrix, right? Those are the same row operations that we would have done for these individual row reductions. What will show up in our columns? Well, for each column of the identity matrix, what shows up when you're done row reducing is the corresponding column of the inverse matrix. So what will show up here is the first column, and then the second column, and then the third column, all the way up to the nth column. In other words, when we're done with this row reduction, we'll have the identity on the left, assuming that the inverse exists, and on the right, well, when you put all of these columns together, you just get the inverse matrix. So all we need to do to calculate an inverse is take the matrix we want the inverse of, augment it with the identity, row reduce until we have the identity on the left, and the inverse matrix will be sitting on the right of our augmentation. All right, so that's a pretty slick trick. So let's actually try it out. So let's find the inverse matrix of this one. So to calculate an inverse, we take our matrix, so minus 1, 1, 1, 0, 1, 3, minus 1, 0, 3, and augment with the identity, so 1, 0, 0, 0, 1, 0, 0, 0, 1. Of course, it's the 3 by 3 identity because A itself is 3 by 3. And now we can start row reducing to turn this left-hand part into the identity. So I guess first multiply the first row by minus 1. That gives us 1, minus 1, minus 1. And when we do these row operations, remember, do the row operations to the augmented part as well. So minus 1, 0, 0. The rest of it stays the same. 0, 1, 3, 0, 1, 0, minus 1, 0, 3, 0, 0, 1. Okay, now it looks like we need to take row 3 and add row 1 to it. So first row stays the same, 1, minus 1, minus 1, minus 1, 0, 0. Second row stays the same, 0, 1, 3, 0, 1, 0. And then third row, we add row 1 to it. So minus 1 plus 1 is 0, 0 plus minus 1 is minus 1, 3 plus minus 1 is 2. And then in the augmented part, 0 plus minus 1 is minus 1, 0 plus 0, 0, 1, 1 plus 0 is 1. Okay, now let's see, next thing to do our reduction, we need to get this minus 1 here to disappear. So we should take row 3 and add row 2. So first row stays the same, minus, while we're at it, why don't we do, to get rid of this minus 1 right here, why don't we also do row 1 plus row 2? Okay, so first row, we're going to get 1, and then minus 1 plus 1 is 0, minus 1 plus 3 is 2, minus 1 plus 0 is minus 1, 0 plus 1 is 1, 0 plus 0 is 0. Okay, second row stays the same, 0, 1, 3, 0, 1, 0. And then last row is third row plus row 2. So minus 1 plus 0 plus 0 is 0, minus 1 plus 1 is 0, 2 plus 3 is 5, minus 1, sorry, third row plus row 2. So minus 1, 1, 1. Okay. And next we need, I guess we need to divide this row by 5. Divide last row by 5, so 0, 0, 1, minus 1 over 5, 1 over 5, 1 over 5. And then, let's see, 1, 1, 0, 0, 2, 3, minus 1, 0, 1, 1, 0, 0. Okay. Now we need to use this third row to eliminate the stuff above it. So let me actually do it down here. We're going to do row 1 minus 2 times row 3, and row 2 minus 3 times row 3. Okay. So first row, 1, 0, and then 2 minus 2 times row 3 is 0. Okay, now minus 1 minus 2 times row 3, so minus 1 plus 2/5 is minus 3/5. 1 minus 2/5 is plus 3/5. And then 0 minus 2/5 is minus 2/5. Okay, now row 2 minus 3 times row 3, so 0, 1, 0. Now minus 3 times row 3, so that's going to be 3/5, 2/5, and minus 3/5. And the last row doesn't change, 0, 0, 1, minus 1/5, 1/5, 1/5. Okay, so that means this right here is the inverse matrix. All right, well, the proof is in the pudding. Let's actually check. Let's multiply things out and see if we get the identity matrix. So our original matrix was minus 1, 1, 1, 0, 1, 3, minus 1, 0, 3. Okay, and our supposed inverse is minus 3/5, 3/5, minus 2/5, 3/5, 2/5, minus 3/5, minus 1/5, 1/5, 1/5. Okay, so now let's do this matrix product, which is 3 by 3, so it's big. Let's see. going first row, first column, we get minus 3/5 plus 3/5 minus 1/5. Having a hard time with arithmetic today. Minus 3/5 times minus 1 is plus 3/5. So 3/5 plus 3/5 minus 1/5 is 6/5 minus 1/5, which is 5/5, which is 1. Okay, now second column, first row, minus 3/5 plus 2/5 is minus 1/5, plus another 1/5 is 0. Okay, third column, first row, plus 2/5 minus 3/5 is minus 1/5, plus another 1/5 is 0. All right, things are looking okay so far. Now, first column, second row, 0 plus 3/5 minus 3/5, so 0, and then 0 plus 2/5 plus another 3/5, that's 5/5, that's 1, and then 0 minus 3/5 plus 3/5, that's 0, and then last row, minus, so 3/5, 0, plus 3/5, 0 minus 3/5, so 0, minus 3/5, 0 plus 3/5, 0, and then plus 2/5, 0 plus another 3/5, that's 5/5, that's 1. Okay, it worked. So we got A times A inverse is the identity of size 3. To be 100% sure that this is the inverse, we really ought to check the other way around, but it turns out that if it's an inverse on the right, it has to be an inverse on the left as well, assuming that both matrices are square. So we see that this row reduction trick really did let us find A inverse. So when you're done reducing A augmented with the identity down to the identity augmented with something, what shows up right here is the inverse matrix.